Okay, welcome to the Cloud Native Buildpacks deep dive. Thank you for burning the midnight oil with us here. And as like one of the last sessions of the day. Everybody's probably pretty tired. I'm tired. My name's Joe Kutner. I'm going to be talking about Cloud Native Buildpacks, which is a cloud native sandbox project in the CNCF. It was founded by Pivotal and Heroku, but we now have contributions from many organizations, including Google, Microsoft, and others. So I work at Heroku. I work on the languages team. Heroku is a platform as a service. We host more than 10 million applications and handle about 23 billion requests per day. On the languages team, we do the engineering work that provides the support for our official languages. And one of the tools that we have to do that is Buildpacks. So Buildpacks, if you've ever used Heroku, you've used Buildpacks. They're the mechanism that prepares an application for running on our platform. We originally created them about 8 years ago as an extension point for the platform so that our users could add or customize the images and add support for other ecosystems and languages that we didn't support. So over time, other organizations adopted Buildpacks, the Buildpack API, and then we started diverging and sort of implementing Heroku-specific things and Cloud Foundry-specific things. And so Cloud Native Buildpacks is an effort to bring those APIs back together and to join them with the Docker container ecosystem. So at a very high level, Buildpacks take source code as input. They detect what kind of application you have from your source code repository. And then they prepare that application for production depending on what kind of app it is. So if it is a Java Maven app, it'll install the JDK, run Maven, download your dependencies, compile your source code. If it's a Node.js app, it'll run npm and download your Node modules. The output of the Buildpacks build is a Docker image that has layers that map logically to your application. This is different from like a Docker image created from a Dockerfile where the layers are arbitrarily derived from directives in the Dockerfile. So because of this well-defined structure and the metadata that goes with it that tells us what's in the layers, we can perform operations that would otherwise not be possible. So the Buildpacks themselves are just one part of the Buildpack ecosystem. In fact, the Cloud Native Buildpacks project does not maintain any Buildpacks. The Buildpack implementations themselves come from third parties like Heroku and Cloud Foundry and others. What the project does maintain is what we call a platform. This is essentially an environment that's capable of running Buildpacks. So the Pack CLI is a sort of reference implementation of a platform. You can use it to run Buildpacks on your local workstation or in a CI environment. We also maintain a Tekton template so that you can use Tekton as a Buildpacks platform. The implementation, or what we call the lifecycle, is the Buildpack execution environment, and we maintain this as part of the project. We also maintain libbuildpack, which is a Go library that Buildpack authors can use to make it easier for them to implement the Buildpack specification. And of course, the project maintains the spec itself, the core APIs that define how Buildpacks work and how it interacts with the different components. We also have an RFC process that we use to propose changes and discuss various changes to the project. So to visualize how these different components work together, at one end of the spectrum we have the Buildpacks themselves, which are the part that actually touches your code and runs against your app. The lifecycle runs Buildpacks, so it's the executor of the Buildpacks. And then beyond that, we have the platform, which is the environment that knows how to put all of this together and run the whole Buildpack system. So between each of these layers, we have a well-defined API, the specification, which describes how these layers interact with each other. And that essentially allows us to mix and match or swap out different implementations of each of these components. So the Buildpacks, of course, we have different Buildpacks for different languages, Java, Node, Ruby, and then from different vendors like Heroku and Cloud Foundry. The platform, I mentioned Tekton and the Pack CLI. There's also the Pivotal KPack project, Salesforce Heroku, and Google Cloud Run Button. There's many other platforms coming around day to day, so a lot of options there. So the lifecycle executes the Buildpack API, and just to recap what we talked about in the intro talk yesterday, This API has several phases. The first phase is detect. This is where a build pack determines whether it should or should not run against a given source code repository. So in most cases, this is just looking at the source code to see if particular files exist. For example, package.json would indicate that it's a Node.js app. The restore and analyze phases are run by the lifecycle, the Buildpack execution environment, and they analyze the cache and then the metadata for previously built run images, if they're available, to determine what layers can or cannot be reused. The build phase is kind of the heavy lifting of the build packs. Each build pack implements this differently. It's specific to the ecosystem that a build pack supports. So for example, a Node.js build pack would install Node.js, run npm, and prepare the Node application for a Node build pack. One of the outputs of the build process is artifacts, or essentially layers. And in the export and cache phase, the exporter, the lifecycle, takes these layers and compiles them into an OCI image. It will take some of the layers and put them in a cache, which can be stored as a cache image or as just like a persistent volume. OK, so that's just kind of recapping the intro. Now we're going to take a very close look at some actual build pack implementations from Heroku, and then Steven's going to talk about some Cloud Foundry build packs. So all the stuff we're going to talk about in this deep dive isn't something you need to know in order to use build packs. If you just want to use build packs, you can run a command like pack build against your source code repository. It produces an image, prepares it for, to run with commands like docker run or to be pushed with docker push. That's how most people will use build packs. But we're going to get into what's going on when you run this pack build command. So the first thing you'll notice is that we're passing a flag to this command, the builder flag, with the Heroku Buildpacks image, and then that's running the Heroku Java build pack. That builder image is an important construct in Cloud Native Buildpacks language. A builder image encapsulates all the artifacts that a platform needs in order to run build packs. So that includes the build packs themselves. It also includes the lifecycle to execute those build packs, and then a base image that will be used to create the container that all this will run in. So we define all of those components in a file that we typically call the builder toml, and we pass that builder toml to a create builder process that produces a OCI image that is the builder image. So if we look at the builder toml for that Heroku Buildpacks image, it first defines the lifecycle version that it is compatible with, and then it defines the stack that it runs on. So this builder image runs on the Heroku 18 stack. A stack is another important term in Buildpack language. Stack represents two images. One is used for build to create the container that Buildpacks run in, and then another is used as the base image for what we call the launch image, which is the image that's output from the Buildpack execution process. So the Heroku Buildpacks are based on the Heroku 18 stack. This is a base image that's maintained by Heroku as part of the Heroku platform. So if you've ever used Heroku, you've used this stack. It runs as part of the platform. It's based on Ubuntu Bionic with some system packages pre-installed that we provide updates for. So you can download this from Docker Hub. There is the Heroku 18 and Heroku 18 build images. The build image contains dev headers and other tools that you need to compile and prepare your app for production. The Heroku 18 image is slimmer and just has only what's necessary for runtime. But in any case, these two images provide the foundation for the Cloud Native Buildpack stack. To create that stack, we have to add a few more layers on top of this. We define a few CNB underscore environment variables. These environment variables are defined as part of the Buildpack API specification. We define the CNB user ID and group ID for the user that Buildpacks will run as. Buildpacks do not run as root. It's a feature. And then the CNB stack ID so that the platform can know what stack it's actually working with. So if you were to create your own stack from whatever flavor of Linux or whatever base image you want, you'd do something similar to this, have your from directive, and then add those just those essential environment variables. So this is the Docker file for the build image. The Docker file for the run image is pretty much identical with just a different from directive. Okay, so coming back to the builder toml, after we've defined our lifecycle and our stack, we then define the build packs that are going to go into this image. So the Heroku build packs include, I think there's about 10 of them in this image. They map to the languages that we officially support: Java, Node.js, Ruby, some others. And then there's a few utility build packs like the Heroku Procfile build pack. And I'll describe what that does in a minute. In addition to the build packs themselves, we also define what order they run in. So when the lifecycle executes the detection phase for build packs, it's going to execute them in the order that we've defined here. And the first one that passes detection is the one that it'll use during the build phase. So we can define individual build packs in our order, or we can define groups of build packs that must all pass in order for that group to succeed. Or we can have, as I'm showing here, some optional build packs where if they fail detection, the other build packs in that group will still execute. Okay, so that's everything that goes into the builder toml for the Heroku builder image. We then pass that to the pack create builder command, which will handle creating the image for us. It'll add the build packs to a well-defined directory. It'll inject the lifecycle binaries. It'll validate that those CMB_environment variables are set up correctly, and do some other stuff to prepare that OCI image so that we can run it. The output is the Heroku Buildpacks 18 builder, and then that is built on top of the Heroku Pack 18 and Pack 18 build stack. Okay, so as I mentioned, the Heroku Buildpacks image contains a number of different build packs that support different languages, but we're going to focus on the Heroku Java build pack. So this is a build pack that's been running in production for many years on the Heroku platform, but with the older Buildpack API implemented. So we wanted to sort of bring this build pack into the Cloud Native Buildpack ecosystem, so we've modified it to support both APIs. Because it's an older build pack, it has a lot of files, but it has 3 files that are essential. So any Cloud Native Build pack must have at least these files. 2 executables, bin build and bin detect. These map to the 2 entry points in the lifecycle phases for detect and build. Those executables can be bash scripts, they can be binaries written with Go, they could be Python scripts. There's nothing in the Buildpack specification that defines how you write these files. They're just executables. The third file is a Buildpack descriptor called Buildpack toml. This defines some metadata about the Buildpack. So this is the Buildpack toml for the Heroku Java Buildpack. It defines its API compatibility version, its globally unique ID, its version, and then what stack it is compatible with. So the Heroku Buildpacks are only compatible with the Heroku 18 stack, and each Buildpack author determines what stacks they intend to support with a particular Buildpack. So the bin detect executable is responsible for that first part of the lifecycle execution phase. It's very simple. It looks at the source code repository, which is provided as one of the inputs to the detection. It looks at that repository for a POM XML. If it sees a POM XML, it'll pass. Otherwise, it will not pass. That POM XML indicates that this is a Java Maven project, and it knows how to build those. One of the outputs of the detection phase is a build plan. So the detect script will add to the build plan the components that it either provides or requires as part of its execution. So the Java build pack is going to provide a JDK, so it writes to that build plan. The JDK is something it provides. Then on to the bin build executable. This takes as input the same source code repository that was passed to the detect phase, and it also takes the resolved build plan. So the resolved build plan contains the components that were provided by the bin detect script from this build pack, as well as other build packs that may have run in conjunction with this build pack. So if we're running, for example, a Node.js build pack with our Java build pack, our resolved build plan might have a Node.js entry in it. So the build pack can look at that build plan to determine what it needs to install or what is available to it. So the heavy lifting of the bin build script is installing the JDK, running Maven, downloading your dependencies, compiling your code, and then producing those Java artifacts that represent the application. One of the outputs of that process is several layers that represent the JDK, the Maven dependency cache, and the JRE. But each of these layers has a different scope, or sort of a different visibility. Some layers will be used as part of the cache because we want them available on subsequent builds. But some of those layers we do not want in that final launch image. In fact, the JDK, which contains the Java-C command, the compiler, and some other development tooling, is meant for the build image only. The JRE, which is the Java runtime environment, is what we actually want in the launch image. So we can define each of those layers as having different scopes. Similarly, for the Maven dependency cache, we don't want Maven in our production image, and the dependency cache is very large, so we only want that in our cache image. The build scope is a little different. It's not actually like a layer that's going to be put into any image. This just means that it is visible to subsequent build packs that may need to use the JDK as part of their execution. Each of those layers has a standard POSIX file format structure to them. So this allows us, or allows build packs to do some things kind of magically for you. Each layer's bin directory will be put on the path. The lib directory will be put on the load path. And then we can also set up environment variables and profile scripts that will be provided as part of the launch image so that when your application starts up, those are there for you, things like Java Home. The last file here is what we call a layer descriptor, or a layer toml file. So each layer has one of these descriptors that goes along with the layer, and it tells us what scopes the layer is for. So for that JDK toml, we see that launch is false because we don't want the JDK in our final run image, but build and cache are true because we do want to expose it to subsequent build packs and cache it. We can also put some metadata in this file, like the version of the JDK that's been installed, and then we have a cache ID that allows us to just easily expire it. So if we compare that to the JRE toml, very similar, just has a different scope for launch. We do want the JRE in the final launch image, and we don't want it as available to subsequent builds. The last thing the Heroku Java build pack does is try to determine the Java command to use to start this app that it can set as essentially as the entry point for the image. It does this by looking at the POM XML, looking at your dependencies. So for example, if it sees a Spring Boot dependency and an executable jar file in the target directory, it knows that some java-jar command is the process you probably want to run. Sometimes it doesn't get it right, or sometimes you want to override that. And that's where the Procfile build pack comes in. So the group in the Heroku builder that has Java includes the Heroku Procfile build pack optionally. The Procfile build pack is meant to support Procfile, which is a part of the original Heroku build pack API, but it's not a part of the Cloud Native build pack API. But for our customers, for our Heroku users, we wanted them, who already have a Procfile in many of their repositories, we wanted to provide that same experience for them. So if you're not familiar with the Procfile, it's just simply a very flat YAML file with a key that is the process type or the process name, and then a command that is the command you want to execute for that process type. So for example, a simple Java app would have a web process type and then a java-jar command to start the app. So the detect script for the Procfile build pack is very simple. It looks at the source code repository for a Procfile. If it sees that, it passes. If it does not, it doesn't pass. It doesn't contribute anything to the build plan because it's not creating or providing any components. The build phase for the Procfile build pack reads that Procfile YAML and converts it into the launch toml process table. So the launch toml derived from the Procfile that I showed earlier would look like this in a launch toml. So because this build pack runs after the Java build pack, if it was to create a process type that was already defined by the Java build pack, it would override that, and the last one would win. So you can use the Heroku Java build pack by running pack build with the Heroku Buildpacks builder, just passing that -- builder option. If you have a Java repository that you're running against, it should detect that and run the Java build pack. But if you want to be explicit, you can also pass the -- build pack flag. Coming in the next version of the Java build pack, we'll be taking advantage of a new feature in Cloud Native Buildpacks called slices. This allows us to sort of carve up the application repository or the application directory into layers without creating that separate POSIX file structure for a layer. So we could, for example, take your dependencies in the target directory and your classes and your config and put them in their own layers as well. We're also going to decompose the Java build pack into at least 2 build packs. A Heroku JVM build pack, which just installs the JDK and the JRE, and then a Maven build pack, which does all the Maven-specific execution. Separating them into these 2 build packs allows us to use the Heroku JVM build pack with other build packs, like, for example, a Gradle build pack, so we can make them more modular so they can fit together in different ways. So now I'm going to pass it on to Stephen, who's going to talk a little bit more about build pack modularity and how build packs are run in distributed environments.
Yeah, so I'm Stephen Levine. I work on things related to Kubernetes and Cloud Foundry for Pivotal. And I'm not going to talk about the Cloud Foundry build packs very directly, but more about how we do builds with the Cloud Foundry build packs in sort of distributed systems like K8s using tools like Pivotal KPack. And so just for some background, Joe covered some of this. Stacks, builders, and build packages are composed of layers. So a stack is a build image where the it's a sort of a base image where the build happens. A run image, which is sort of the runtime base image for the application. If you take the build image and you put a lifecycle and some build packs on it, you get a builder, right? And so a build package is just sort of the artifact format for a build pack. So if you're talking about the Cloud Foundry Node.js build pack, it's actually a series of sort of 3 build packs in a particular build configuration that it's composed of. It's not sort of implemented as a build pack itself. It just points to those other ones. And a build package lets us sort of take all those build packs as layers, package it up in an OCI image that you can either push to a Docker registry or save as a .cnv file. That's sort of the artifact format. It's like a fully self-contained build pack. And if you take that build package and put it on a build image with a lifecycle, you get a builder. And so that's sort of what that builder image looks like. And then if you take the builder and you run source code, you sort of run the builder in a platform with the source code like KPack, you get an app image out the other side. And so I'm going to kind of run through what it looks like to do a rebuild of an application in a distributed system and focus on the kind of rebuild time and the data transfer required, because it sort of exposes why we think this model is really interesting for doing really fast iteration against a cluster. And also, there'll be a second example afterwards that shows you how we can roll out CVE patches really quickly for lots of applications. But we're going to do the first one first. So if you imagine you have a Docker registry. A Docker registry stores manifests, which are image manifests, and layers, which are they're also called blobs. They're just the things that get layered on top of each other before they run. When you do a Docker run, for instance. Say you have a Docker registry with a run image, a build image, and a node build package, and then you have sort of all the layers that those manifests point to. The layers aren't sort of linked to each other. The manifests just define an ordering of those layers. That's kind of a common misconception. In the Docker v1 format, the layers are kind of linked, but now in the OCI or Docker v2 format, the manifests just refer to a particular ordering, and we can swap them out individually, and you'll see what that looks like. And so if we can make a builder by essentially just creating a new manifest in the registry that has sort of strong references to the layers in the build image and the build package, and kind of a weak reference to the run image, so we know where to pull a run image when we do a build. And because this is just a manifest upload, it involves virtually no data transfer. We're just uploading less than a kilobyte of JSON configuration to the registry to say, hey, this builder is composed of these parts that already exist. And so when we want to do a build, we need to download the builder and the associated layers to the VM that's going to run the pods that do the build. And if a build already happened here that was a Node.js build, that doesn't involve any data transfer because it's already there. The pod is already, or the VM is already hydrated with those bits. If the VM is a fresh VM that's never done a Node.js build, you might have to download some of the build packs. And so if we kind of ignore the builder in the registry, and let's say that you did a previous build, of this application where you have an old version of the app image in the registry, pointed at sort of old application layers and the operating system packages, and then you also have a local cache sort of in the VM that we're doing a build of the same application. Because in a distributed system, you'd want to try to rebuild on the same VMs that you're building so that you can sort of get more cache hits. Sort of in that configuration, we would start a pod in the VM that runs the builder, which has a lifecycle inside of it, on the source code, which we would have to upload. But the build packs, when they're run by the lifecycle, can actually look at the old layers from the previous application build in the registry and say, I only need to rebuild these individual layers. I don't have to rebuild, say, all the node modules or whatever it might be. And then during the build process, the lifecycle runs the build packs to regenerate just those new layers that need to change. And it also updates the cache with whatever sort of new things need to be cached. This is kind of different from Docker, where in a Docker file, if a sort of lower level layer changes, you have to rebuild them from the top. Here, we can individually select what layers we want to rebuild. And so, after that happens, we update the cache and the sort of local VM, and we upload the sort of newly built dependency layers to the registry, along with the sort of new manifest for the application. Notice that it's reusing a lot of existing sort of dependency layers in addition to the new ones that it uploaded. So we've really minimized the data transfer there to just rebuild what needs to be rebuilt and just upload the new stuff into the registry. And then when we switch over to the runtime VM that's running the old copy of the application, we can sort of apply the new image manifest, which will cause the new layers and just the new layers to transfer over to the runtime VM, not additional base layers, nothing that was sort of already there from the previous application. And then restart the pod so that it is running the new application. And so that was an example of what it looks like to rebuild an individual app, right? But there's some kinds of updates we can do with Cloud Native Buildpacks where we want to patch CVEs for lots of applications at the same time. And we can do this at the operating system level because we rely on a sort of strict ABI compatibility contract where we can we call it a rebase instead of a rebuild, where we're replacing the lower layers with a strict contract that gives us a guarantee, I guess, that the new image is also a valid image and will run, but also contains security patches from operating system vendors. And so this works imagine you have a Docker registry and you have 3 apps in it. Maybe you have the run image that they were built with, pointing at the operating system packages, and then a CVE hits. And so now all your apps are vulnerable in the registry. Maybe you have 3, maybe you have 500 apps, right? To sort of patch that CVE, we can upload a single copy of the operating system packages to the Docker registry. So think of that like you're uploading Ubuntu 18.04, like a new version of that has a patch to OpenSSL or something like that. And then we just make a kind of really small update to each of those image manifests to point at the new operating system layer without really incurring any other data transfer other than that initial upload of the operating system packages to the registry. And so now we've patched all the apps on the registry kind of instantaneously. And so we still have to deploy that out, right? It's not done. Yes, we've patched all those applications, but now they have to run in a cluster. But the way we've done this kind of allows us to deploy these really efficiently as long as they're using containerd and not Dockerd. Dockerd is very inefficient and will repull layers on top of base layers if they change, even if it already has those layers. But containerd can do this really efficiently. And so this works so imagine you have several runtime VMs with different apps distributed across them, and they all are vulnerable to the CVE. We can transfer them, essentially do a Docker pull into each of those, or containerd pull into each of those runtime VMs, which will cause the new operating system packages to get downloaded and the apps to kind of swap around automatically on each VM and point to the new operating system packages. Note that we only had to download 1 copy of the operating system packages per VM, not per application. And so it's sort of maximally efficient in transferring just the layers that have the CVE patches to each VM that needs to run. And you wouldn't be able to do this in a model like Docker, where you'd have to retransfer, you'd have to rebuild on top of a new base image, and then retransfer all the newly built layers across. So this is something you can do really fast, and it even extends into deployment. And so to kind of wrap it up, We really like cloud native build packs because we think they're reusable, and the build packs are reusable. They reuse dependencies, they reuse layers. They're sort of very efficient in how they do data deduplication. They're fast because they only rebuild the stuff that's necessary. They're modular because you can create individual sort of modular build packs that are very single purpose. And they're safe because you can get build packs that are trusted by a vendor that knows what they're doing and can guarantee that they're sort of configuring your app in a secure way. And that's it. Please try out the Pack CLI. It's up on Buildpacks.io. We have docs available. You can also join us on Slack. We're really active on Slack, so please reach out. We also have a mailing list, but it's pretty quiet. There's going to be some Buildpack demos later today at the Salesforce booth, too, if you want to talk to us more. Thank you. Questions? There.
So you're taking out layers, but some of those layer changes might require a pod restart or container restart. How do you handle that?
Yeah, so the question is, we're changing these layers out, but the layers will handle in order to get the layers to run, you'll have to restart your pod with them, right? So we don't, for what Cloud Native Buildpacks does, we don't handle anything after the updated images in the registry. We want to kind of solve that one problem really well. But what we do is, by sort of efficiently only updating the layers that need to change in the registry, when you do that pod restart, you'll only get those layers downloaded onto the VM. And so by the nature of how we publish it to the registry, we can make that deployment process really fast.
So you're basically putting it after this image gets updated, restart the pod.
Sure, yeah, you can do that with the CI/CD system. We've tried to solve just the problem of let's get it to the registry and stop there, kind of solve one problem well. But the way we do that does make it really easy to use tools to promote it through a CI pipeline, whatever you want to do with it. Restart your pods and get it deployed out really quickly because of the data deduplication there. Over there.
What would be the best way, for example, to reuse the Gradle Buildpack, but also pass it some additional flags or run whatever rate has?
Yeah, it depends on the build pack. So the Heroku Gradle build pack uses well-defined environment variables that it will pick up and then either apply Gradle ops or something like that. I can't remember some of the specifics. The Maven build pack, similar functionality, but with different environment variables. So it's really up to that build pack. Some build packs could have their own manifest or descriptor that they would read in. The Java build pack actually does this with a properties file that defines the JDK version to install.
Yeah, it looks like most of the stuff in the bin folder is usually like bash, right?
So the Heroku build packs are primarily written in Bash. They're using Bash as a controller to drive smaller, sharper binaries in most cases. I think the Cloud Foundry build packs are 100% written in Go. Is that? Yeah.
In the front? Further back, sorry.
So you mentioned that the previous way Buildpacks worked was you would have all of the build dependencies would have ended up in the final deployed image. I think it's true of Cloud Foundry and Heroku, right? Whatever was getting downloaded during the compile stage of the Buildpack would ended up being deployed and run in the end result. Does it mean you've made breaking changes in some ways that people had expectations of GCC was there and the final result they could provide in their application? Has that ever been a challenge?
Yeah, so the question is, in the old build pack model, we used to build on the same sort of build image and run image, and now we have separate build images and run images, right? There is a little bit less of a guarantee in doing that, in that if you're not very careful about what those images contain, you could end up with something that's missing during runtime. The guarantees we care the most about are that on updates of the run image, it's ABI compatible, and on updates of the build image, to newer build images, right, it's ABI compatible. Between those two images, it doesn't matter quite as much for a few reasons. One is if your app doesn't start sort of immediately, you have fast feedback, right, between those two things. The other is we can be really careful to make sure that we only include things like compilers and we only exclude things like compilers in the run image, that we don't have C libraries that something might link to on the build image that aren't on the run image.
The running image is quite large with the build packs that you guys created. It's like, I know that previously Heroku was just getting 700 megabyte image out of the result. The running image is still quite large with the base build packs.
They're whatever the, so the question is about the size of the, those base images. They're whatever the platform that provides that image decides. So for Heroku, I think it is about 500 megs, and we've chosen to make it larger to include more things because it's part of our platform. It's like what, it makes it a better experience for our customers to have those things available. But I think Stephen has done some work on smaller images.
On the Cloud Foundry side, we have a choice of 3 images. So one is like a large image that is 500 megs or so for linking node modules that might have native dependencies, things like that, right? But we also have like a 20 meg one that's just Ubuntu Bionic essentially with compilers in the build image. We even now have one that has a distroless run image. That's our own kind of roll of distroless on top of Ubuntu. That's almost as small as Scratch. It just has glibc in it, I think. So you can make really small images, especially if you're building with Go. We've really optimized that use case on the Cloud Foundry side, so you can end up with something that's a sort of Scratch-like convenient image in the end. So you shouldn't have problems with that. But in addition to that, you can also create your own custom stacks that have your own kind of set of build packs in them. You just have to make sure they maintain compatibility with the build packs, right? Cool. In the front?
So I'm trying to get my context right here. I'm thinking about, okay, I have a Java build pack. Does the same one work on both Heroku and Cloud Foundry? And would I be able to say use it somehow in Jenkins, or do I need to add like some wrapper stuff to make it a build agent for Jenkins?
Got it. So the question is about build pack compatibility between platforms. Where is it that you can only use Heroku build packs on Heroku and Cloud Foundry build packs on Cloud Foundry? The answer to that is if you just look at the new Cloud Native Buildpacks v3 project, that lifecycle, build packs that run on that lifecycle are always compatible across all different platforms. So there'll be real complete compatibility. You can run the Cloud Foundry build packs on Heroku, the Heroku build packs on Cloud Foundry, and we're even starting to invest in defining our stacks so that you can mix and match Cloud Foundry and Heroku build packs within the same build, potentially in the future too, although there's still a lot of discussions about how we want to do that. So the compatibility is really great. We're pushing even more in the direction of more compatibility between them. But we do have some kind of different use cases for build packs. Like on the Cloud Foundry side, we've always really liked the ability to do completely offline builds. On the Heroku side, they offer more different versions of the dependencies, right? And so we have some reasons why we maintain different build packs, if that makes sense.
Yeah, I think it depends on what you mean when you say like on Cloud Foundry or on Heroku. Like that could mean like you're running on the Heroku cloud platform, but it could also mean that you're using the Heroku build packs with the Heroku builder image in some other like pack or some other platform. So.
In the back there?
So I saw that you guys have multiple stages that you guys started. Is there also an opportunity to provide custom stages in the build packs or no?
So the question is, that we listed these stages like detect and build and analyze and export. Can you inject custom stages into that process? And the build packs are kind of those custom stages, if that makes sense. During the build process and each build packets have been built. During the detect process, each build packets have been detect. We have thought about some additional hooks into the process for things like expiring the cache really early if you're on a platform that implements remote cache instead of a local cache, like in the examples. So I think we're definitely open to more of that extension, but it's already very extendable because that's kind of the point, right? But that's a good question. In the front here?
How do build packs interact with the Cloud Native application bundle? Like, does it interact well with the spec?
Yeah, so the projects, even though they seem similar and they're kind of named similarly, they kind of don't really overlap. So Cloud Native Application Bundle is about sort of a way to package and deploy images and configuration for like things like a bunch of KTML and a bunch of images you've already built into a cluster. Cloud Native Buildpacks is about building application images. So they could interact really well. You could use Cloud Native Buildpacks to build images, which you then ship with CNAB. We actually do that right now for KPack, where we're building KPack itself with Cloud Native Buildpacks and then distributing it via CNAB. Yeah, so the question is, OCI images are immutable, and so how are we making these sort of swapping changes and dealing with those immutability constraints? Is that kind of the question?
Upstream, like an application would reference a Buildpack version or something, right? Like an application repository.
Yeah, okay, so I'll try to address that, and let me know if I'm kind of covering it. So when we generate a new manifest that points to a different selection of layers, it's essentially a new image. It's a new, the old image continues to exist and refer to a selection of layers. We're creating a new manifest that has a different digest and refers to some of the layers the previous one did and new additional layers, right? And so it does preserve the immutability of the model, if that makes sense. But it's careful to bring along layers from previous builds so that we get that data deduplication. If you're talking about how we handle immutability with referencing build packs, so that build package construct is an OCI image, and it has hard references in its manifest to the individual build pack layers with their, yes, with an ID inversion inside of them, but also with that SHA-256 sum that describes the layer. And so the build package can act as sort of a distribution format where you get those strong guarantees of, yes, this is an immutable thing. If it changes, you'll know about it. Does that sort of answer the question?
I don't think so, but we can take it offline.
Yeah, it sounds good.
It's more about like an application repo, how an application will pull in the Buildpack, and you're saying you can do this without having to, rebuild everything to get the build part, but it's like somewhere some application team is going to have to update their versions for the base image updates or that.
So like, how do you use, maybe your question is, how do you use cloud native build packs in a more declarative way where the updates kind of are stream out into applications for you so you don't have to know when to rerun pack build, that kind of thing? So that's what Pivotal KPack is, a project that provides a declarative API for saying this is where my source code is, and that's basically, this is where the image should live, and then it monitors for all the build packs and stacks and does rebuilds automatically. It provides a sort of declarative interface into cloud native build packs. So you should check that out if you're interested in kind of solving that problem. It's open source. Okay.
Is there an option to bring basically your target binaries instead of having Buildpack do the build for you? We do a lot during our build phase that goes beyond what the Buildpack would typically do. At the end, a jar file may be finished, and I'd rather just take that and run it through a Buildpack.
Got it. So the question is, is there a way to use build packs to sort of do less of the build process, like build a jar file first and then provide that? So as an example, the Cloud Foundry Java build pack is actually a selection of 40 or between 10 and 40 different build packs, depending on the distribution of it. And if you provide source code, it will turn that into a jar file first. If you provide a jar file, the build packs that compile the source code will kind of flip themselves off during the detection process and say, nope, I'm not necessary, and they're marked as optional, so they're not going to fail the build, and then the other build packs will take it from there. So you can kind of throw whatever you want at that thing, and it will figure out what to do with it, if that makes sense. But in a modular, kind of transparent way, not like, it's some big blob of complexity that's hard to understand what's happening. Cool. Over there.
How hard do you think it will be for organizations that are trying to adopt this model to start using Buildpacks? Will it take a lot of trial and errors and things like, proliferation of a lot of different Buildpacks or where organizations will build it? Or do you feel there will be utilization will be vendor?
Both in the Cloud Foundry and the Heroku side, we want to provide a sort of rich variety of build packs covering lots of language ecosystems. So if you're okay with using those build packs, the build packs you write are just going to be small tweaks you need to do to the build process that should be easy. And there are a lot of tools out there that Pivotal's written, that Heroku's written already, that use cloud native build packs to provide solutions to make it really easy to adopt them. So the goal there is that it should be much, much easier to adopt cloud native build packs in your organization than it would be to create your own selection of pipelines and Dockerfiles and base images and all of that. It kind of automates that process, gives you a lot more visibility into what's going into your applications. It kind of solves that problem for you with a managed system, if that makes sense.
Yeah, I think particular challenges at the moment you start forking the Buildpack, right? You're starting to add small modification and then you don't maintain the
Yeah. Well, so the modularity we have like I said, the Cloud Foundry Java build pack is a lot of modular build packs. It allows you to do things like make a small build pack that just overrides some behavior or swap one out, right? It's a JDK build pack and a Maven build pack and a Gradle build pack, or it's a NPM build pack and a Yarn build pack. It's not a giant Node.js build pack anymore, right? And so that was a problem we really had with the old style build packs that we really think we've kind of provided a nice solution to here. But we're definitely looking for feedback and want people to try it out and tell us.
Yeah, I think it depends on how you want to adopt build packs. You can use the third-party build packs from Cloud Foundry or Heroku, and then you have to accept the constraints of like, this is the stack that Heroku works with, right? You can also create your own build packs, which if you have your own constraints, like we're only working with this JDK vendor on JDK 8, whatever, the build pack may be 100 lines of bash code, which by comparison to something like Dockerfile is you get to write that build pack once and use it on all of your apps as opposed to having Snowflake Docker files. So I think the answer is kind of it depends.
Any other questions? All right, thanks everybody.